So my name is Alexander Krzyżanowski. The most of work which I will be talking about is done by Evgeny Mekhanik. Unfortunately, he could not attend the conference, so I'll be talking on his behalf. So what HP streams are about? To figure this out, it's probably the best way to figure this out is to use the web page test resource. This is just a regular website. You can enter any web address and run any test for any browser with different connection quality, different places. I already run the test. The test for Netdev conference page looks like this. The interesting point for the report is this time break. And in this time break, we see that almost 4 seconds, the web page is unavailable. We just see the blank screen, and then for 4 seconds, we start seeing something. And the most of the content is also depicted about 4 seconds. This name is largest contentful pane. Next, we can open any report, and we see the waterfall. And in the waterfall, we see that there's only one HTTP connection, this HTTP2 loading. And on this HTTP connection, there are a bunch of resources loaded, like HTML, CSS, JavaScript, and so on. With HTML, we have a dependency and broken resources. For example, there's no sense to load CSS before HTML is loaded, or run JS before CSS is loaded. So the order of resources is important, and all the resources are executed in separate HTTP streams. So we have only one connection and many HTTP streams for each of HTTP requests. Next stream is largest contentful pane. It's green line. It's about 4 seconds. So it's very important to load all the resources important for largest contentful pane as early as possible. Basically, any business website do care about HTTP because there's the quality, there's user experience, and actually Google search bot also cares about HTTP. Okay, next, what we had in late 23 when we started to improve our scheduling mechanism in Tempesta. HTTP scheduling is well studied. There's at least 2 academic research done by Robin Marks. There are 2 LFC standards, 7540 is outdated and 9218 is presented since June 22. And this was like 1.5 years since LFC published it. So at the end of 23, it appears that 7540 is only used for HTTP2, and 9218 was used for HTTP3. So we said, okay, that if nobody supports 9218 for HTTP2, then we'll do the same. And we started to work on the 7540. About 7540 is dependency tree. The main feature about LFC is dependency tree. Let's have a look what is dependency tree. We also can build a dependency tree, observe the dependency tree on web page test, and we see, for example, the stream for HTML, stream for CSS. CSS depends on the HTML, a bunch of JavaScript, and CSS depends on CSS, and so on. So this dependency tree. The streams on the below depends on upstream. What else we need for prioritization? So one thing, we have a dependency. So a dependent stream must be loaded after the parent stream. Next, we have a wait. In 7540, we have a wait. In 9218, we have urgency, more or less the same things. We have a reprioritization. It means that any stream, any time can change its parent, the dependency can change its weights, and so on. So dependency tree is always time is rebuilt. Next, we have idle streams. I will talk about them a bit later. And the thing point about this is that we break the dependency rule. So when we start to load web resource, we have at this point we have a bunch of resources. Web browser sends, for example, 10 or 20 HP requests to intermediary server. For example, it could be CDNH, and the CDNH can distribute the request among upstream servers. And upstream servers can return response for dependent stream before the parent request is processed. So at this point, we can decide whether to be RFC compliant and postpone the response until the parent stream is available, or we just send what we have so far and let browser to collect them. Next, a bit more about the representation. In both standards, done with priority claimants. Weight change is available for both the standards. Dependency tree is only for 75, 40, and on the stream, on the slide, we have a case when stream A is made dependent on stream D. So if it's non-inclusive, it goes as a child for D and shares bandwidth with stream F. However, if it's exclusive, it means that it cannot share bandwidth with any stream. So it has the exclusive bandwidth, and stream F make a child of A. Relatively complicated operation, but this is what we have. Let's have a look what Firefox 125 does. Firstly, it establishes all the stream as idle, and immediately with creating new stream, it sends representation frame. So representation happens very like for HP request. For most of the requests, it's just about changing weight from 0 to something more meaningful, but about 1/3 of requests also change dependencies. So the dependency tree is going to be reconstructed. However, as we saw on our dependency tree, we see that the most of the streams are actually not a tree. This is just a linear list of dependencies. So on each dependency level, we don't have any choice rather than just to send one particular stream. The only difference is, for example, for stream 5 and stream 7, we see that they have common parents, and we can distribute bandwidth between the streams. For example, stream 7 has weight 256, stream 5 is 220. So stream 7 is more prioritized, and it will be sent with a bit more priority. However, if we have a look, remember that the stream 5 is stream 7. If we have a look on web page test console, we see that, the stream 5 is exclusive headsheet, and stream 7 is also exclusive. So this RFC contradiction, the streams cannot share the same parent. In our understanding, this is just a bug in web page test that when representation happens and when new exclusive stream appears, web page test doesn't handle the case and does not rebuild the tree. So essentially, in this place, we don't have a sharing bandwidth, have a wider list. What next? So what we see for now is that essentially for most of the resources and most of the browsers, we see just a linear list. We have a sequential request. We first receive one request, after that another, and third, and so on. So essentially, we don't have any multiplexing in HP tools. The resources loaded sequentially. However, there are several exceptions. For example, progressive JPEG, Firefox browser behaves completely different. And we have also GHTP2 client code, for example, in H2 load benchmark, which does create not exclusive streams, and so we have bandwidth sharing based on the stream weight. What progressive JPEG, I think everyone saw web pages when it's load, which pictures in bad quality, and after that the quality becomes better and better. We would assume that such resources, when you have thousands of images like eBay, YouTube, when you have a video preview images, Google Chrome will use progressive JPEG. However, it turns that it's not true. Progressive JPEGs are very resource hungry, and modern resources like this one on the site actually use IP, more recent image format for plain JPEG. So we didn't find any progressive JPEGs in the wild in large resources. Next exception is Firefox stream prioritization. Actually, Firefox don't use exclusive slab, so we have a real prioritization as it's supposed to be in HP2. We have actually streams multiplexing. We see dark purple. It's essential phase when the image is going to be uploaded. The bright purple is when we just established the stream. Dark purple is when the loading happens. What we see at this moment is that this is a very bad strategy for Firefox, and this is why only Firefox uses this strategy. If you assume that we use a strict round robin and just send piece by piece for each of the images, we'll finish at some time loading all the images, and those images will be loaded at the same time. And this is much worse than we just pick any random image, load it as soon as possible, then next one, and so on. So the median time will be much better for real HTTP stream scheduling. Okay, what else about Firefox? Firefox is the only browser which uses idle streams as the placeholders in dependency tree. In our understanding, this is done, also Robin Marks reported this, that probably done to avoid bad conditions on dependency tree. For example, when child stream changes dependency, but the parent stream is deleted, so we have a race between assigning the streams, and this we need placeholders. However, the Firefox is unique in this property. Other browsers solve this in different manner. Yes, Firefox does a lot of representation frames. Let's summarize the difference between the two RFC which we have at the moment. So 7540 is outdated, but it's only used for HP2. HP3 doesn't use it. HP 9218 is used only for HP3, and it has very similar implementation, but much simpler. There's no dependency tree. Urgency is just like weight, but if weight in HP2 is about bandwidth sharing, in 1992-18, urgency is about the audience. It means that resource with urgency 0 will be loaded earlier than resource with urgency 1. We also have opportunity to share bandwidth. It's for incremental flux, just like with explicit clock in 7540. So when we started to work on this task, we wanted to just borrow some compatible licenses codes in our project. So we started to explore open source implementation. So firstly, we had a look at Nginx. This is a snippet for the code for scheduling HTTP streams. The bottom line is about weight. So Nginx just compares the stream's weight and downloads the image with the figure weight. So it means that it does not make any bandwidth sharing, just uses weight as ordering. This is compatible with 9218. but it's actually 75-40. Maybe Nginx developers realizes that most of the browsers do not share bandwidth, and Firefox does a poor job on scheduling streams. Don't know. And also the rank is actually dependency. For Nginx just check dependency of the current stream, but it does not check that more the parent dependent the parent stream already sent all the data when we move to dependent stream to send data. So it's not fully RFC 75-40 compliant, so we move to another implementation. That was H2O. H2O uses amazing schedule which works for constant time. It's a deficit-based algorithm, and it works on approximated version of weighted fair queuing algorithm, and uses 64 uncles. It's like a hash table, and it puts priorities to the bucket, so it can make mistakes on sending actually different streams which became in the same bucket in uncles. So we wrote a simple Python verification program which just emulates this algorithm, verifies with a more theoretically correct one. Truly, it's not a strict theoretical verification, and especially it's not a real-life setting, but we saw that sometimes the algorithm can make mistakes in prioritization. Another thing is that due to using the array of hash tables, uncles, the scheduling data structure is about 1 kilobyte. So each stream in H2O weighs maybe about 2 kilobytes. It was too much in our understanding, so we wanted to get actually more fair schedule, probably as fast as H2O. Next implementation is HNG HTTP 2. It's a library. It's used by Envoy, Apache, HTTP, and a lot of other open source projects. It uses real weighted fair queue with the data which is aware about the sent data, not only about the frames. However, it uses utility data structures, binary heap, just to manage dependencies and fetch the next stream. In the binary heap, just copies insertion operation, so it seems to us not so fast as H2O. So we wanted to get something closer in performance like H2O, but more fair like in NG-HTTP2. So we formulated the requirements to data structure to our schedule. We realized that in most of the times we never schedule more than 100 streams, even for very sophisticated pages. Single dependency tree level doesn't work with a lot of streams. So typically we schedule very small number of streams. Reinsertion operation is the most common operation. So we pick some because the next stream to send from the data structure, recompute its index by the algorithm of weighted fair queuing, and reinsert back to the queue. So reinsertion operation is the most frequent one. We consider different data structures suitable to schedule small amount of HTTP streams, and we ended up with the elastic binary trees used in HA proxy and developed by Viritareo. This unique hybrid data structure, which is essentially a radix tree with binary radix tree. So each layer of radix tree is essentially moves to left branch or right branch based on the current bit. So like for the key for 32 bits, it has a level of 32. It's essentially imbalanced, and another property is that it's intrusive data structure. It means that it does not allocate happen data, happen intermediary index nodes in separate memory, but always keeps the happen index nodes together with the leaf node. So it's very efficient in terms of cache locality. Since it's embedded binary tree, and in worst case it's just a linked list, in average case it's still binary tree, it's very efficient for small datum. And it's actually used by HAProxy for scheduling. So we made a micro benchmark. We also considered Fibonacci heap because of amazing insertion time, constant time. But in benchmarks, we could not make the Fibonacci heap fast enough to beat any of the other implementations. So we stuck with the elastic binary tree. Next, about the algorithm itself, about the weighted fair queuing. Kazuhoko, developer of H2O, had a good presentation about HTTP2 stream prioritization, and he made a good example about naive weighted fair queuing approach. So, for example, we could have two streams, A with weight 10, B with weight 5. We can just incrementally decrease the weight, current weight of A, and when it's equal to B, we start to send B. Both the stream has 4, we start to decrease, and when we reach 1, we start C. It's by then it sends all the streams. However, at the beginning, like half of the time, it's going to send only stream A. It's naive, it's not good. There are a lot of research in different weighted fair queue algorithms, but most of them have more or less the same idea about penalty. The similar approach is used in the modern Linux kernel shader EVVDF. It's log, but in NG-HTTP2 it's penalty. H2O doesn't use penalty, and it works only on frame granularity. It means that it uses the current stream to send, packs the whole frame, and the whole frame, and don't care how much that actually was sent by each of the streams. So it works on the frame granularity, not about the bytes granularity. And HTTP2 uses penalty, which uses last sent is the number of bytes lastly sent. And it computes the cycle. Cycle is essentially the order which stream is going to be sent next. The minimum value wins. So as more weight, then we have a less value. So it's reverse proportional to weight, and it's proportional to penalty. As more data we send, the more cycle, and we're going back to the queue. So you compare, try to compute, and for example, in A and B streams, send different number of bytes on each of the iterations. By then, we see that A sends twice more data as B. So we went with this approach like NG-P2, and that's not the end of the story. 1 week ago, Firefox released finally 92.18 support for HTTP2. Chrome did this in April. And that's not the end of the story. We actually did not implement the 92.18, and we are not alone. The only NG-HTTP2 implemented this standard in full. H2O and Nginx didn't support don't support this protocol extensions yet. What's new in Firefox 1.28? It sends the settings NoRFC 7540 priority, means that we gave up 7540 and we're going with the new standard. It continues to send weight, exclusive flag, and also to this property, it also sends the urgency and urgency flags for 92.18. And previous two versions of Firefox work exactly the same, but they don't initiate the new protocols. They just work if server proposes it. In Tempestive Double, we still in progress of this work. At the moment, we have a logarithmic scheduler. We have better memory locality. We wanted to get something closer to performance as H2O, so we worked a lot on better memory locality. We pre-allocate streams when a new HTTP connection established. We use two system pages to pre-allocate streams. We use intuitive elastic balanced trees to do page locality. We also have a bunch of special optimization. For example, as we see that in most of the cases we don't have any scheduling, and we have the pure dependency list. In this case, we don't compute deficit. We don't compute deficit. We don't reinstall into the data structure. And just go with the dependency tree. Also, we have a configuration option. So if in HP2 you have a web resource which do use progressive GPF, or maybe you need some web API which actually uses the concurrent HTTP stream, then you can switch the option on, and the TPS will behave like in FC 9218 and just send use stream waste as ordered. Lastly, we TPS works as a part of TCP/IP stack, so it knows about the current TCP state. The HTTP routines are called from callback from TCP write exmit TCP write lookup. At this point, we know the available congestion window and the announced tick window from the peer, so we can produce the optimal size for HTTP frames and TLS records. We don't send too small TLS records and TLS frames. We have much more data to send. The last topic is about security. The first CVE is pretty old. It's 2015, and it's about building dependency tree. So if we have a dependency tree and the leaf depends on the root, so it's assuming that the schedule will spin forever and so on. However, in RFC, this clearly stated that in such case, if we have a dependency cycle, we need to repent to the service stream 0, and it seems that the CVE is only applicable for non-RFC compliant implementation. Another more recent CVE is about priority frames. However, in general, we would say that HTTP 2 and HTTP 3 come with service frames with like ping, settings, priority, and so on. So it means that you can not only produce the HTTP flat, but also ping flat, priority flat, setting flat, and so on. So typically, implementations come with rate limiting for service frames, and also on reducing, limiting the depth of priority tree. So that's all from our side. The code is available on our GitHub, and also we have a wiki page which we publish Python scripts, some snippets, some research about browsers, and we'll update the page with the development of this stuff. So I'm ready for your questions. Thank you for listening.